In this lecture, we will go over the CFA Level 2 reading on correlation and regression. Quant has 3 readings. This is the first one, and it is, in a sense, the simplest one. If you are not good with numbers or you've not done much statistics before, you might have some challenges, but if you stay with me, have a little bit of patience, try to understand the most important points first before getting hung up in the details. The details will come later. You need to obviously know some details to solve the problems, but make sure you get the core points first. At a high level, this reading will first talk about correlation analysis. This will build on what you saw at level 1. Half of this is what you've already seen. The other half of this section is new material. And then linear regression. Regression has been alluded to at level 1, but here you will actually get into regression. In this particular regression, we will only worry about one independent variable. In the next reading, we will worry about multiple independent variables. Okay, let's start with correlation analysis. Here are the subsections in section 2. And again, all these numbers are based on the curriculum. We'll talk about scatter plots, the basics of correlation analysis, how to calculate and interpret the correlation coefficient. We've seen this at level 1, so this is a recap. What are some of the limitations, the uses? Nothing too new over here, but as I mentioned earlier, we will actually take this information and go a little deeper into how and why this is useful. And from a testability perspective, this is critical, testing the significance of the correlation coefficient. Okay, so I will highlight this as perhaps the most testable aspect of section 2. All right, first a very basic idea of a scatter plot. A scatter plot is a graph that shows the relationship between the observations of 2 data series in 2 dimensions. If we take a very simple scenario, and this has been taken from the curriculum, where we have several countries, we don't really need to know what the countries are, but somebody looked at 6 or 7 countries and saw whether there is a relationship between money supply growth rate, something that you study in economics, money supply growth rate and inflation. All right, so level 1 economics, hopefully you remember a little bit that there is a relationship between how your money supply grows and inflation. You don't need to know the economics of that over here, but let's say you are an analyst and you want to say that, okay, the economists are saying this, let me look at the data and test whether there is any relationship. One of the most simple things you can do is a scatter plot. So you say money supply growth rate on the x-axis, inflation on the y-axis, you collect data over a given time period for several countries, and you come up with a plot like this. So visually this tells you that there appears to be a relationship. As the money supply growth rate is higher, the inflation rate is higher. So this is one useful and very simple tool. Okay, next, section 2.2 in the curriculum is correlation analysis. Hopefully you remember this from level 1, but I will refresh your memory. And this excerpt is from the curriculum. Again, as I mentioned before, what I'm doing is taking out the most important aspects of the curriculum. The correlation coefficient is a measure of how closely related 2 data series are. In particular, the correlation coefficient measures the direction and extent of linear association, and this is very important. Correlation is a measure of linear association between 2 variables. A correlation coefficient can have a maximum value of 1 and a minimum value of -1. You are looking at a picture here where there is variable A on the x-axis, variable B on the y-axis. What do you think the correlation is between A and B?
1.
The correlation is 1. There is perfect positive correlation between these 2 variables. What about in this scenario? Again, variable A on the x, B on the y. So here the correlation is -1. Perfect negative correlation. And what about the third picture over here?
0.
Here the correlation is 0 because there seems to be no relationship between the two variables. Fairly straightforward, so I won't spend much time on this. Okay, next, this is something you've seen at level 1, but it is part of your level 2 learning objectives. How do you calculate the correlation coefficient, and then how do you interpret it? I'm going to describe this at a high level. As I said, it is part of your learning objectives, but I think the probability of being tested on the mechanics of this is low. Nevertheless, since it is part of the learning objectives, I will mention what needs to be done. So you have two variables, let's say the money supply growth rate and inflation rate, and you want to calculate the correlation. The first thing that you have to do is compute the covariance. And this formula might look familiar. This is how you calculate the covariance of a sample. All right, your two variables are x and y. The first thing you do is calculate the average of x, which is generally denoted with a bar. So x bar is the average of x. You calculate the average of y for every data set. So remember, correlation means that you are taking a value of x and a value of y, and then another value of x and another value of y. So you look at a particular value of x denoted by xi minus the average value, multiply that with a particular value of y minus the average of y. So you multiply these two out, and then you sum. So this is the summation sign. You sum up all these products, and since we are dealing with a sample, you then divide by n minus 1, and that exercise is done over here. You can see this once in your life. I would not have you spend too much time on this. If you must, then you can do the practice questions at the back where they make you do this calculation. All right. You also calculate for each sample the variance. So this is the sample variance for x, and then similarly you calculate the sample variance for y, and then the sample correlation, generally denoted by R, is given by this expression, the covariance which you calculated over here divided by the standard deviation of x times the standard deviation of y. So fairly mechanical, not worth spending too much time here on this, but as I said, if you've not done this before, do it at least once in your life. All right. What are the limitations of correlation analysis? Correlation assumes that we have a strong linear relationship. So if you have two variables a and b and they are related like this, for example, is this a strong relationship? It is a strong relationship, but it's not a linear relationship. The correlation here will be effectively 0 because the correlation number is only looking at whether there is a linear relationship. Correlation can be unreliable when outliers are present. So if you just look at the calculation we just did, if you have data that is sort of like this, there will be a particular correlation. But let's say in a given country, if you are looking at the relationship between money supply and inflation, you have a number that's way out there, huge outlier. Will this impact the calculation? It will. You saw the mechanics. So if they are outliers, they have a large impact on the calculation of correlation. And finally, you can have something called spurious correlation, which simplistically is accidental correlation. This can happen for one of the following reasons. The correlation between two variables that reflects chance relationships in a particular data set. So you have two data sets, you run the correlation, and just by chance, coincidentally, it turns out that there appears to be a good relationship. How do you detect this? Sometimes where there is no economic explanation for why there is a correlation, it just might be chance. The other scenario is you might have correlation induced by a calculation that mixes each of two variables with a third. And finally, correlation between two variables arising not from a direct relationship between them, but from their relation to a third variable. There is more detail on this in the curriculum. For now, what I'd say is from a MCQ perspective, as long as you learn these points, you'll be in good shape. Next, section 2.5 gives us several uses of correlation. There are many examples. So example 1 through 6. Depending on how much time you have, you can quickly read through these examples. There aren't too many calculations, but I have included relevant aspects of each of these examples in the slides. When you have time, or if you have time, you can look at these examples. If you have questions, post them on our group. And if I feel that there are issues that people are having, then I'll create a video lecture for these examples. But the point that you will notice is that this correlation analysis is an important thing to do, and it is used quite often in finance and investment related activities. Okay, now we come to section 2.6, which, as I mentioned earlier, is extremely testable. Before I go into the details here, the high-level principle is this. You have two large populations. Like, for example, you might have if we are talking about the relationship between money supply growth and inflation. So simplistically speaking, your population would be, the population correlation would mean that you look at data for a very long period of time, let's say forever, since the two countries existed or since the data existed. But practically, when you try to solve for correlation, you won't take the population data, you will take a sample. So just because you get a particular correlation by looking at a sample, can you trust that correlation number? We don't know. So we don't know, therefore we will need to do some hypothesis testing. And largely this builds on what you saw at level 1, but there's one twist, which is going to be this formula that I will talk about. So this actually is the first formula, new formula that you are learning at level 2. Okay, let me go through this more formally now. Significance tests allow us to assess whether the apparent relationship between random variables are the result of chance. And what we are going to do now is use hypothesis testing. If we go back to our example of money supply growth versus inflation, let's say that you pick 4 countries or 5 countries and you come up with a certain correlation number of 0.8. Is this statistically significant? The way we do this is we set up a null hypothesis. The null hypothesis is generally what we want to reject, if you remember from level 1. So we set up a null hypothesis that rho is 0. What does this mean? This is generally we use the Greek symbols for population, right? So we are saying that let's set up the null hypothesis that the population correlation is 0 versus an alternate that the population correlation is not 0. Is this a one-tailed test or a two-tailed test? This is a two-tailed test because we are using a not equal to sign. So equal to and not equal to. If we had a greater than equal to, then this would be one-tailed. Okay, so again that connects back with level 1. So we set up this null hypothesis. What do you think we want to do now? Do we want to reject this null hypothesis? Hopefully. So we actually have this number from our sample. This is the R. Do you remember from level 1 that when we are talking about a sample, then we use the regular English letters? Okay, so R represents the sample correlation. How do you figure out whether to reject the null hypothesis or not to reject the null hypothesis? If you recall the steps, one was you set up the hypothesis, the H0 and the alternate. Then you would come up with a test stat, and you learned several formulas for test statistics, and then you would compare at a given significance level. All right, so we've already done the first thing. We've come up with the null and the alternate hypothesis. The second thing now is to come up with the test statistic. For this sort of a test, where you are determining whether your sample correlation really can be trusted, you use this test statistic. So this is T, the test statistic, is equal to R. What is R? Sample correlation. Square root of n minus 2. What is n? The number of observations. Okay, so each observation is actually a paired observation, if you recall. So correlation by definition is between two variables. So it is the number of observations divided by square root of 1 minus r squared. So I'm going to pause here for 5 seconds. I want you to stare at this formula, write it down, mark it. This is an important formula to memorize. The test statistic is r into square root of n minus 2 over square root of 1 minus r squared. Now we are going to go through an example which illustrates this point, and I'll actually discuss this example because I think it is very testable. Okay, we are testing the correlation between money supply growth and inflation. As a side remark over here, when you go through the curriculum, you will notice that the readings build on the examples. So they talk about money supply growth rate earlier, and then the examples are based on what they talk about. Plus, the examples are all very relevant. So if we are talking about probability or correlation, they will not pick random examples from other industries. They'll all give you examples that actually connect with what is of interest to you. And given that you are pursuing the CFA charter, presumably finance and investments is of interest to you. Okay, so earlier in this reading, we showed that the sample correlation between money supply growth and inflation was 0.87. So is this R? It is, because that was based on a sample. Suppose we want to test the null hypothesis H naught. So what is the null hypothesis now? That the correlation of the population is 0. So how do we write that? This is equal to 0. Then what is the alternate hypothesis? That the population correlation is not equal to 0. Now this is a big number, so that might lead us to believe that we can reject the null, but we can't just do it that way. This is a big number, but what about our sample size? The sample size n is only 6. Since it is not a large sample, it's actually a small sample, then maybe this was just an accident. Alright, so now what do? We compute the test statistic, and this is the formula. Do you see this as an application of what you just learned? So the test statistic is equal to, this is the R, square root of n minus 2 over square root of 1 minus r squared. So what is your test at? It is 3.532. What is the next thing we do? Given the level of significance, we need to come up with the critical value. And from level 1, recall that you have a small sample over here. So do you use the z test or the t test? Which table do you use? You use the t. Okay, with the t, you need degrees of freedom. At level 1, you generally used 1 degree of freedom without thinking about it. Here, since we are using a pairwise correlation, so we actually have at t equal to 6 with n minus 2, so we have 4 degrees of freedom. The reason is the degrees of freedom here is n minus 2, because we are dealing with two variables. So if n is 6, then n minus 2 is 4. That means that degrees of freedom is 4, and that is what you look up in the t table. We are not going to look up the t table here. I assume that you already know how to do that from level 1. Okay, so we look up the t table, and at a significance level, so if the significance level is 0.05, this is the same as saying confidence level of 0.95 or 95%, the critical value is equal to plus or minus 2.776. Again, this comes from the t table. So if you go back again to level 1, if you recall, so you have minus 2.7 and you have plus 2.7. Where is the test statistic falling? The test statistic is over here, to the right of this. So do we reject the null or do we not reject the null? So this is reject the null zone. This is also reject the null zone. So we can reject the null hypothesis. And that means that there seems to be some statistical evidence. All right. And then I've included this text which you can read, but effectively if you followed what I said, you have grasped the main aspect of this example. Actually this is example 8, but this is testing the relationship between, the corona yen return correlation. It's interesting. If you have a chance, read it. But again, the key will be that you have that same formula. Notice a difference over here without even reading everything. Is that R number? What's the R number looking at this? The sample correlation. 0.286. This is a relatively low correlation. But is it statistically significant? What's the test stat coming out to? It is pretty high. How come? So chances are you will reject the null, because here is another thing that you learn at level 2. Unless you are told otherwise, mostly the level of significance is 0.05. That seems to be the default. And generally for a reasonable sample size, this will, for a two-tailed test, mean a rejection of plus or minus 2. You'll do enough of this and these numbers will just stick. So clearly you can see that this test stat means that you will again reject the null. So notice that with a relatively large sample size, what is n over here? Just by looking at this, even without reading all the text. N is pretty big. When you have a large sample, then even with a low correlation, you can get statistical significance. If we had this small number with only a sample size of 6, chances are that we would not have been able to reject the null. And then more of the same. Okay, this is example 9. They give so many examples on this, and I've seen in past mock exams this shows up, so that's why I'm emphasizing this. And then again another example. All these examples have this formula, and in this particular case there is no statistically significant relationship because this number is less than 2. Alright, we are done with correlation. Now we will talk about linear regression. Alright, so with linear regression we have several subsections. This is section 3 in the curriculum. We will go over this high-level discussion of linear regression with one independent variable, and in fact this whole reading is with one independent variable. You will have to learn the assumptions behind the linear regression model. Then over here we start getting into an alphabet soup. There will be these terms that you just need to learn, and I will try to explain it in a way that makes it easy for you to learn. So there will be something called the SEE, standard error of estimate. There will be a coefficient of determination, which is also called R squared, which is also called multiple R. So if you are not careful, this becomes very confusing. But if you are careful, you realize that the underlying theme is not that complicated. We will do some hypothesis testing again, and then we will get into something called ANOVA, which is the analysis of variation. This is critical, almost a guaranteed question on the quant part of your exam. Then we'll talk about prediction intervals and limitations of regression analysis. So that will be it in terms of your first reading. All right, linear regression with one independent variable. I'll read the basic definition from the curriculum. Linear regression allows us to use one variable to make predictions about another. So that is one utility of linear regression. Test hypotheses about the relation between two variables. That's another utility. And quantify the strength of the relationship between the two variables. Alright, so that's what linear regression is used for. As with correlation, linear regression assumes a linear relationship between the dependent and the independent variables. Is this hard to remember? That linear regression assumes a linear relationship. Okay, if you have trouble remembering that, then we'll have a larger issue. Okay, so that is something to know. The dependent variable is generally denoted as a y, and the independent variable is generally denoted as x. The form of the regression equation is shown over here. So we are saying y is the dependent variable, and when we say I, that means a particular instance of y depends on b0, which is a coefficient, b1, which is another coefficient, and these are called regression coefficients. Depending on the regression that you do, these coefficients will have their own name. For example, when you are regressing the returns of a stock with the returns of the market, then this b1 is actually the beta that you have studied at level 1. And then this xi is a particular instance of the independent variable, plus an error term, and then this is for various i's. So for x1, x2, x3, for each of those there'll be a corresponding y1, y2, y3. All right. Now, what do we try to do in regression? There is, you might find an example where this is all worked out, but in general, more important than the mechanics is understanding the concept. So we are looking at our same relationship that we've talked about: money growth rate on the x-axis and inflation on the y-axis. What do you think is the dependent variable and what's the independent variable? This is your independent variable. So the money growth is independent, because if you are a researcher, what you are saying is, if you remember from economics, the hypothesis is, or the theory is, that inflation depends on money growth. So there is a economic justification also to setting it up this way. Somebody who doesn't really understand economics might set it up the other way, which will be a mistake. One of the biggest things in regression actually is to set up the form of the equation properly. Fortunately for us, this will generally be given to you. Okay, so in any case, we are given x, which is money growth rate, and the dependent variable, which is inflation. You might recall the scatter plot. Simplistically, the regression line is the best fit line through that scatter plot. That's the simplistic statement. The more complicated mathematical statement is that we are trying to minimize this value. This might look complicated, but it's not that bad. All this is saying is, what does yi mean? Yi is like this would be x1, this would be y1, this would be y2, so x2, y2. So yi represents the different instances of y, minus b0 hat. The hat always refers to an estimate. So when you run the regression, the software will tell you that the estimated value of b0 is this. That is denoted as b0 hat. Okay, so just quickly with symbols, whenever you see a bar, what does that mean? Average. When you see a hat, that means estimate. Okay, so b0 hat minus b1 hat into xi. Doesn't this look like the regression equation? It does. So this part, the part that I have marked or underlined in red, for a given value would be this thing over here. This is what the regression equation is predicting. So the difference between yi, what's yi? Yi is this. So what we are showing here is this distance, effectively the error term. So what we are doing is taking the error term, squaring it. Why are we squaring it? Because if we don't, then it will just cancel each other out. Sometimes it will be positive, sometimes it will be negative. We are squaring it and adding up all those squared numbers. The appropriate values of b0 and b1 are such that this expression is minimized. that is what your regression software is doing. Fortunately, you don't need to do this. Your regression software will do that for you. All right. Here in section 3.2, you need to memorize the assumptions behind linear regression. And this is very important because there will easily be a question on your exam which asks you to regurgitate this information. The first is that the relation between y and x is linear in the parameters b0 and b1. What do you think this means? All this means is that if we have y is equal to b0 plus b1 x plus an error term, linear in parameters b0 and b1 means that you do not have things like a b0 squared or b1 cubed. So this doesn't happen. b0 and b1 are just raised to the power of 1. You cannot also have things like b0 over b1. Not allowed either. So we just have the very simple form of b0 and b1. X is not random. The independent variable, you actually pick different values of the independent variable and then see what is the dependent variable. Expected value of the error term is 0. If you look at our previous scenario, so you have a given scatter plot and then you have the regression line. The error term might be positive at times, it might be negative at times, but the expected value needs to be 0. That's assumption 3. Assumption 4 is that the variance of the error term is constant. In other words, you should not have a situation like this, where initially the error term is like this, and then you have something like this. What is happening to the variance of the error terms? It is increasing as x increases. The assumption with linear regression, or to accept a linear regression, the variance of the error term needs to be constant. This is not saying that there should be no variance. There has to be some variance, but that variance should not be variable. So the variance in of itself needs to be constant. And when that is the case, this situation is called homoscedasticity. And just to throw out a term that you will need to know later, when this doesn't happen, if you have a situation where the variance is not constant, then that's called heteroscedasticity. Okay, strange terms if you've not heard them before, but you are hearing them now. Assumption 5 is that the error term is uncorrelated across observations. Okay, what does this mean? Uncorrelated means that you should not be able to predict the next error term based on the previous error terms. Like what I've shown over here actually seems to be a violation, because it seems like one error term is positive, then the next is negative, then the next is positive. So you can potentially predict the next error term based on what you're saying. So there is some sort of correlation. So that also has a name, which you will see later. But at this point, understand the logic or the concept that the assumption of linear regression is that the error terms are uncorrelated across observations. And finally, the error term is normally distributed. So at level 1, I hope you learned to love the normal distribution. It keeps coming up. Just to check your understanding, if the error term is normally distributed, what do you think the expected value should be?
0.
It should be 0. Okay, and then there will be some variance around 0. At this point, this assumption is not saying anything about what that variance needs to be, but the assumption is that the error term should be normally distributed. Let's take a very quick look at example 11. I do want you to read this on your own, but I'll just make a few high-level remarks. Here what we are doing is taking predicted values of inflation. So we have predicted value of inflation as indicated by the CPI versus actual. What is the independent variable? The predicted. And what is the dependent variable? Actual. You are a financial analyst and you rely on the inflation predictions of your economic unit. Does that sound like something that is related to the real world? It is, because lots of large institutions will have their economists. Now, might you be interested in how good are these guys at predicting? Right? So you want to understand whether the predictions are a good indication of what has actually happened in the past. So you can run a regression. If the predictions are good, and now let's go back and create a basic form. So y is equal to b0 plus b1x plus an error term. If the predictions are accurate, then b0 should be 0 and b1 should be 1. Okay, that would imply that there is power in these predictions. And what the curriculum shows is it takes a particular scenario and it shows that in this particular case, given the data, the predictions were actually quite good. They came up with a B1 of approximately 0.9. You won't end up with exactly 1. And then you can do a hypothesis test to test whether that is statistically different from 1 or not. Okay, so when you read the example, it will be fairly self-evident. So I've included the entire text over here. Just read it. Okay, next we come to the standard error of the estimate. This is also called SEE. The standard error of estimate measures how well a given linear regression model captures the relationship between the dependent and independent variables. So we are saying that there is a relationship. We have a regression line. How well does that regression line capture the relationship? Okay, now this again might look complicated, but I'll try and make it simple for you. In this particular regression, we are looking at monthly total returns of the S&P 500. This is our dependent variable. And we are trying to look at the relationship between that and inflation. And notice that these examples connect with what you've seen at level 1. Is there a relationship between inflation numbers and stock returns? Probably. Remember, inflation, expected inflation is built into the discount rate, which impacts stock prices. So now that you have this powerful tool, you know how to do regression, or you know how to interpret regression results. You say, okay, let me just run a regression and see whether the data confirms my belief that there is a relationship between the two. So you collect the data as indicated by the scatter plot. You have your quant guy run the regression, and this is what you get. Okay, now the question is, how well does this regression model, the regression model is the line, the regression line, how well does it capture the relationship between the dependent and the independent variables? And that is measured by what? Something called the standard error of estimate, or SEE. It is unlikely that you will be asked to calculate this, but nevertheless, you should still understand where it is coming from. This is what you need to memorize. This is more likely, it is more likely that you'll be tested on the concept. But what are we doing? If you look at this relationship, this is saying that the summation of what? Of the various error terms. What are the error terms? So the error terms are showing the difference between the model and the actual values. All right, so you take all those error terms, you square them, and then you divide by n minus 2. Since it's a sample and we have pairwise correlation, you divide by n minus 2. Remember, when you are doing just a sample variance, what do you divide by? N minus 1. That is because you are just dealing with one data set. Now, since you are dealing with 2, you divide by n minus 2. And then you take the, since you've done a square over here, you take the overall expression and take the square root. All right. Now, clearly, if you had a relationship like this, and you have a model, the model is the line, and the dots are the actual data, is the SEE here high or low? Here the SEE is low. Whereas another relationship where you have data that is sort of like this, and this is your line, here the SEE will be high. So simplistically, will you be happier with a high SEE or a low SEE? You will be happier with a low SEE. A low SEE means that your model is doing a good job of indicating the relationship. All right, so this is the first acronym that you need to remember. And remember this well now, because there'll be another acronym that looks and sounds a lot like this. All right, example 12 is something you can do. I think the probability of being tested on this is relatively low because it's fairly mechanical. It is using the process that I just described to actually calculate the SEE. So notice we are doing the square, the residuals, the square, and then on the next part of this example, we'll actually run through the calculation. Okay, you can read this if you have time. Okay, next one, and this is very important from an exam perspective. You've learned SEE. Now we are talking about the coefficient of determination. In a way, this builds on SEE. The SEE gives some indication of how certain we can be about a particular prediction of y using the regression equation. But SEE still does not tell us how well the independent variable explains variation in the dependent variable. So it tells us something, but it doesn't tell us quite enough. So we need something more. That something more is the coefficient of determination. This measures the fraction of total variation in the dependent variable that is explained by the independent variable. Total variation is equal to unexplained variation plus explained variation. Now, what does this mean? Okay, I'll give you a picture that is not 100% precise, but will give you a sense for what we are talking about. X is our independent variable, Y is the dependent variable. Let's say that you have a data set that looks like this. So this is your scatter plot. You then have your regression guy run a regression, and there is a line that is produced. This is your regression model. Okay, now what do we mean by this thing called explained variation and unexplained variation? If you look at these various y values, there will be a certain average value of y. So all these y values, if you just take out the average of these 1, 2, 3, 4, 5 numbers, there will be a certain average value denoted by y hat. All right, and then based on your regression model, let's say that this value of x is 10. If your x value is 10, what is the number for y which is predicted by the model? That is this thing here, right? So if you tell the model that, look, x or the independent variable is 10, then the model will tell you that the dependent variable is this number. And let me just give some numbers to explain. Let's say that this number is 70, just picking random numbers here. So the model is saying that if x is 10, then y is 70. Let us also just say that based on these various y numbers, the average value of y is 50. Again, picking numbers to illustrate a concept. All right. When we talk about total variation, the total variation refers to the difference between the actual value of y and the average value. Let's say that the actual value of y is 75. So the total variation is this distance. It's the distance between the actual value of y and the average value of y. Now that total variation has two components. One part is this, which is explained by the regression. That's called the explained variation. Why is it called explained? Because it is explained by the regression. And then there is a part which is not explained. Okay, so there is explained variation, and that which is not explained is called the unexplained variation. Now there will be some squaring issues and other issues, but conceptually this is what we mean by explained variation, unexplained variation, and total variation. Now in a good regression, what do you think r squared should be? Should it be high or low? given that R squared is explained variation divided by total variation. So a high R squared is good, because a high R squared is saying that most of your variation is explained. Explained variation based on, the formula is simply this, or mathematically you can also write this as 1 minus unexplained variation over total variation. So all these are just simple terms. Okay. Now, a few other testable points that I want to cover. In this particular reading, we only use one independent variable. When that is the case, when you only have one independent variable, then the R squared, so this, by the way, this coefficient of determination is the R squared. So it is sometimes written like this, sometimes it's called the coefficient of determination, sometimes it's written like this. Okay, so with only one independent variable, R squared is the square of the correlation. So with one independent variable, you just have X and a Y. So the R squared is simply the correlation number, which is R, and square it. But this is not the case when you have more than one X, which is what will happen later. So that is why when you have more than one X, then you need to use this method. This method works with only one X or multiple X. This is the more rigorous method. Another term that you need to learn here is multiple R. The correlation, this R, is also called multiple R. Now I know this is annoying, but I'm doing this with you because I see questions where this material, they test you on basic terminology like this. And those who don't like all the complicated formulas at least nail these questions. Okay, so all the points I made over here are important. Make sure that in your fact and formula sheet you note this down. Alright, now let me quickly test how well you are following this. You have two possible scenarios: low R squared, high SEE, and high R squared, low SEE. Which one is better? Clearly high R squared and low SEE. Now what I want you to do before I do this is, in your notebooks, just with X and Y, just draw out a scatter plot that reflects this situation and then a scatter plot which reflects this situation. So here is what you should be coming up with. A low R squared and a high SEE is a bad thing. So you might have a situation like this over here, where you have a regression line which doesn't do a great job of explaining the actual data. And high R squared, low SEE, this is a good thing. So here we are saying that we might have a regression line which does a good job of explaining the data. Now, here is another exam type question. Let's say that you have a situation like this, where you have data like that. Okay, so some data that is aligned. So, and then the regression equation gives you something like that. Then you realize that this actually was an accident. And you then from your data set remove this. What will be the impact on R squared? Will the R squared increase or decrease? Increase. The R squared will then increase. What will be the impact on SEE? Decrease. This will decrease. Now these are the sorts of questions you are more likely to get on the exam, because they are testing whether you really understand what those terms mean. Okay, so here in example 13, I'll not spend much time on this, but you can go over it if you want. It is giving you the data. We are still looking at the money supply growth rate with inflation, and we are using the mechanism that I just talked about to come up with the R squared. Now here is a question. Let's say we come up with the R squared, and then we take the square root of the R squared. If we take the square root of the R squared, what should we come up with? R. We should come up with R, which is the correlation. and they actually go through the mechanics. This is the r squared, and going back to your basic class 8-9 maths, when you take the square root of this, will you get a number that's larger than 0.7 or less than 0.7? If you take the square root of this, you will get a larger number. Remember, we are less than 1 over here. Right? So you will actually get a number that is larger. And what will that number be? That number will be the correlation. And this only works when you have one independent variable.